So for the last 100 years, we've kind of accepted that all velocity is relative to each other, and that we cannot determine which object is stationary and which object is moving. And we've kind of just assumed that to be true. Now, I made a video about determining absolute velocity in a dimension where there are no stars or planets. All we have are two ships that are moving with respect to each other, and through calculations of different amounts of length contraction, we're going to figure out which ship was stationary and which ship was moving. Now, that leads to me kind of wondering, now, if I can figure out which ship was stationary and which ship is moving, can I possibly come up with an equation to calculate an object's absolute velocity? Okay, so how is that even possible? I mean, the Earth is on rotation around the Sun, and the Sun could be moving in a direction as well. How can we possibly determine anything's absolute velocity? How's that even remotely doable? And let's just look at a scenario in which case, imagine that you are on this spaceship, AB, and this ship has a length of 1. Now 1 could be 1 kilometer, 1 light year, it doesn't matter. And what you see is you see P, which is a point, an asteroid, or whatever, moving towards you in a certain velocity. Now, in this example, P does have a velocity relative to you, but we don't care about that because P could be moving, and all we're doing is trying to find what absolute velocity that we're at. Now, if we're taking a look at this from the first moment, it appears that it would be impossible to figure out our absolute velocity. Or is there even an absolute velocity exists in this scenario? Again, all we know is we have P moving towards us. And again, it doesn't matter what velocity this is. It could be moving towards us at half the speed of light, or slower or faster. It doesn't matter because as far as we know, P could be moving. And if P is moving, then we cannot measure P's velocity to figure out what we're actually doing. Remember, you're in a dimension where there are no planets or stars. There's no way to determine if you're stationary or moving. All you know is you have P that is moving in some direction towards you. Okay, so the reason why I have true measurements here is for us to have a way of verifying if my answers are correct, if my equation is correct. Again, if my equation is being used in a real life scenario, then obviously we would just measure distances and use those distances to calculate our absolute velocity. In this regard, we're going to have used true measurements to show what exactly is happening and to verify our answers. Okay, so what exactly is going on here is that there's a 10 light year or 10 gap between P and A. P is a point in space. Again, this space can be moving. A and B, their ship is moving this way to the left at 0.6 c. So that is what's happening. If we're omnipotent beings, I can see exactly what's happening in this system. Now, P could be moving it, or it could be stationary. It really doesn't matter. So A and B, they have an absolute velocity of 0.6 c to the left. For my equation, we need to find out this value here, 0.6 c. As long as our number matches that, that'd be correct. Now, let's look at what exactly is happening. From A's perspective, A just sees this. A sees a point in space that could be moving some velocity towards it. It really doesn't matter. And B is seeing the same thing. If we have this information, how can we possibly determine absolute velocity? In fact, we're not even taking account the A and P's relative velocity. We don't even need to know that. Because again, because P could be moving, so as long as P is moving, then we cannot use that to ascertain our true velocity. We'll have A make a measurement to P, and we'll get that number as 8. Now, where does that number come from? Remember, the true measurement is 10. So if A is moving at 0.6 c to the left, this 10 distance gap will length contract to 8. So just make sure you get where that number comes from. Because of A's motion to the left, this distance contracts in length to 8. Length contraction. Remember, A is the center point of that length contraction. So this distance will contract to the right to 8. Okay, now let's look at B's perspective. Now B, however, measures a different number. So because B is 11 units away from P, right? So 10 plus 1 is 11. Now when B measures it, B also experiences length contraction. So the 11 distance that goes from B to P, length contracts to 8.8. Okay, remember, A measures distance of 8 because 10 contracting, length contraction at 0.6 c is 8, whereas B sees a length contraction of 8 to 8.8. In fact, 11 multiplied by 0.8 is 8.8. Okay, as you can see right there, we have an asymmetry in different interpretations. See, now this gap distance that B interprets A has is now 7.8. Now, why is that? Well, B interprets itself as being 8.8 away from P. But B also sees A as being 1 away from itself. So naturally, this gap distance that B interprets between A and P is 7.8, whereas A interprets 8. It's with this difference that we can figure out what our true velocity is. Well, let's take a look at the length contraction calculation. So I've just redrawn the diagram where I put the variables in. So A primed is A's interpretation of distance to itself, right? This is the contracted distance. Now A with unprimed would be the true distance. B primed is what B interprets P's distance to itself. L is the length between A and B. Now remember, this doesn't have to be a ship. This could be two separate ships. As long as they have a length difference between them, we can use their different interpretations of length contraction. Now, we know the equation L primed equals L times this value, square root of 1 subtract V squared over C squared, where L primed is the contracted length and L is the real length. Okay, right now we know the contracted length, but we don't know the real length, and we're looking for V, velocity. So in this case, we have two unknown variables, and we only have one known. Naturally, we cannot solve this. Except, keep in mind we have two separate equations, because we have two different answers from A and B. So let's break that down again. So by dividing this down and just changing it around, we have L equals L primed over the square root of 1 subtract V squared over C squared. Okay. Remember, we have our secret weapon here is that we have two different interpretations. We have B primed and A primed. So let's take that look again. So this would mean A equals A primed divided by 1 over, this square root here. And B also equals to B prime over 1 over the square root here. But taking a look at this, again, we're still missing the key variable. We don't know A or B, and we don't know V. So naturally, we have two unknown variables, except we know A's relation to B, because remember, B is just A plus L. Okay, again, so we know A primed and B primed, and we're trying to find V. We don't know A and B. But we do know that B equals A plus L. So we simply sub this A plus L into this B equation here. So A plus L equals B over B primed over the square root. Then we move L to the right, and now we just have to solve for V. And we do that by merging the two equations together. Remember, we have these two equations, and we merge them together. Because A equals this, and A equals B primed, this equation here, but A also equals this equation here. So we can simply substitute this into this, and we get this equation. And now it's just a matter of algebra of moving things left and right. And you guys can kind of go through it or do yourself on a piece of paper. But ultimately, what happens, we get the final equation here. V equals C multiplied by the square root of 1 subtract B primed subtract A primed squared over L squared. Remember, B primed and A primed are the measured distances from B and A. L prime is the distance in between A and B. Again, A and B do not actually have to be on a single spaceship. They could be two separate spaceships. As long as they're moving in uniform motion with each other, we can use their calculations. And now it's just a matter of plugging everything in. Remember, B primed is 8.8. Well, A primed is 8. Remember, so A primed is the distance that A measures between itself and P, while B primed is the distance B measures between itself and P. So when you plug this in, you get 0.6c. In fact, this is so simple, you can actually do this in your head. Take a look. So 8.8 subtracting 8 is 0.8. 0.8 squared is 0.64. 0.64 divided by L squared, which is 1 squared, would of course be 0.64. When 1 subtracts 0.64, that becomes 0.36. And 0.36 square rooted is 0.6. Multiple, again, there's a multiplication by c, so the result is 0.6c. Okay, that is pretty groundbreaking. Okay, so you're going to now be wondering a very, very obvious question. How in the world can two observers on the exact same frame of reference see different things? I mean, for what we understand is that if they're on the same frame of reference, they should see the same thing. They should agree on time dilation and length interaction. And the answer is yes, but that's not exactly true. They do agree on time dilation, but take a look at what happens when we have length interaction in space. for a moving observers. Okay, now remember, when an object is moving, however, the length interaction occurs to the observer, not the center or any sort of that object. So, as I said, A and B could be two ends of a ship, or they could be two completely different ships in space that just happen to be moving in uniform motion with one another. It doesn't make a difference. So let's take a look at what exactly they see. Now, let's suppose that this is A, who's on this 2, and B is on this 2. Okay, so that could be you and your friend Bill. Again, you're on the 2, you're on the center of this ruler. Now, this ruler represents your viewpoint of space. Now, when you're stationary, what happens? The two viewpoints line up. No, A and B, they are one distance away from each other. Now, notice how all of these things are lined up, right? So 3 is 1 away from 2, and from this 2, 3 is also 1 away. And again, see, the 3 lines up with that 4, 2 lines up with this 3. Now, this is all well and good. Notice how everything's aligned, right? Same frame of reference, they see the exact same thing, they see the exact same distance. What happens when these rulers undergo length interaction? Again, these two ships, or this one single long ship, starts to move to the left. These two rulers will naturally contract, right? Because from the observers on these ships, the entire universe will contract in length. Let's just see what happens when that length interaction happens. Okay, here we go. Now, notice from 2 is still aligned with 2, right? Because that's the center point of that length contraction. 2 is here. So 2, or B here, sees length contraction through its center. But A, or 2, or this 2, is also aligned with that 2. And notice how it also length contracts. But notice, now although they're still aligned with their original selves, again, this is an example where let's suppose that they were stationary and now immediately they start to move to, let's say, 0.6 e. Now, but notice how they are no longer aligned. Whereas 1 and 2 were aligned on the same line, 1 and 2 are now misaligned. Similarly, 2 and 3 were aligned, and now they're also misaligned. Notice that there is now a gap. And this is the gap, that's the key point. The reason why there's a gap here is because the two rulers, or in this case, the observations of the space, contract in length along their own observation points, along the points of the observer. Because they both contract, and both observers are in different points in space, their length interaction occurs slightly differently. Yes, the length interaction ratio is the same. The length itself is the same. But the positioning is no longer the same. As you can see, by simply contracting these two rulers, these numbers are no longer aligned. But notice, the gap between 1 and 2, the gap between 2 and 3 are equidistant to each other. Because again, these gaps are constant. Because they're moving at the same velocity, they have the same gap, but there's still a gap nonetheless. Notice, it's this gap that we use in our formula to calculate our absolute velocity. Because guess what happens when you move faster? The faster you go, the more length interaction you occur. And what happens? The gaps get bigger. Notice how, when stationary, when moving, and when moving really fast. Notice how this gap is so much bigger than this gap, and there's no gap here at all. And it's this gap that we can use to calculate our absolute velocity. Again, the faster you move, the more length contraction, the bigger these gaps are. Now notice how when A primed measured 8, B prime measured 8.8. Now, the distance between A and B is 1. So therefore, the B measures the gap distance of 7.8. So that'd be B primed gap, or B interpretation of A's distance to P. So B thinks A is closer to P than A thinks A's distance is. So B thinks this is 7.8, A thinks this is 8. Now, let's take a look at the ruler. Combine these two values. So notice, B interprets the object is closer than A does. Now, taking a rulers. Now remember, B will be the further object and A will be the closer one. So, B is up there. So, assuming let's say the object is at point 0 from B's perspective. So, the faraway object. And that will be at 1 on A's perspective. So this is where the object is, where my mouse is. Okay, now, when length interaction occurs, then from B's perspective, B's the top ruler, remember? This object will move all the way here. From A's perspective, will move all the way down here. Notice how now there's a gap. B thinks the object is closer to us, closer than A thinks the object is. So there is the gap. Again, this same gap shows up earlier. Again, see that? See the gap here? So B, the object, the observer that's further away, sees this as closer than the observer that's closer to the object. Okay, so let's take a look at what happens if the measurer, B, is actually not 1 length away from A, but 0.5 length away. Well, let's take a look at this. So again, A primed will still be 8. Now, we just define B primed. What is B primed? Well, we know that right now, in real space, or in true distance, this would be 10.5 away from P. And we simply take into our equation here, L times this number here, and we get 8.4. In fact, if you want to make it easy, we already know this number is 0.8 from when we calculated the length contraction for A. So we just have 10.5 multiplied by 0.8 equals 8.5. And again, we just plug everything into this value again. Okay, and we just create another equation. Suppose B primed is 11 and A primed is 10. This is what we call the true measurements, assuming nobody's moving at all. Or in this case, if A and B are not moving. Now keep in mind, P could still be moving in this scenario. If A and B aren't moving, then naturally B will see the real distance, which is 11, when A will also see its real distance, which is 10. B sees 11 because 10 plus 1 is 11. And we just plug that into the equation. Now, what happens? So 11, we can do this in our heads. 11 subtracting 10 is 1. 1 squared over L squared, which is 1 squared, is also 1. 1 subtracting 1 is 0. Square root of 0 is 0. So the velocity becomes 0. So when A and B are moving, and you plug in those values of A primed and B primed, well, technically, it wouldn't even be primed because this is non-contracted distance, you get a 0. Now, if we go to the other one, again, 10, 10. B is 20, A is 10, 10. So 20 subtracting 10 is 10. Squaring that is 100. But at the bottom, L is also 10. This L is 10. This squared is also 100. 100 over 100 is, again, 1. 1 subtracting 1 is 0. And yet again, we get a velocity of 0. A and B in this scenario are stationary. So, as long as we have two observers that are reasonable length away from each other, and they can measure distances to a certain point, again, in this example, P could be moving, it could be stationary. It doesn't matter because we're not using P's velocity in any of these equations. All we know, what we do know, is the measurement from A to P and the measurement B to P. With these two values, we can calculate our absolute velocity in space. So let's take a look at this when L is 10. Okay, well, again, everything can be done in our heads. We don't even need calculators for this. If B to P, the true distance is 20, then when length contracted at 0.6c, that becomes 16. Well, effectively, it's just double what A's distance is. So since A has a distance of 8, A primed is 8, then B primed must be 16, right? Because it's just twice the distance to P as A is. Okay, so then we just have this very simple calculation. Again, we can, do this in our heads. A primed equals 8, B primed equals 16, L equals 10. So how? So 16 subtract 8 is 8. We square that, that becomes 64. L is 10. L squared will be 100. 64 divided by 100 is again 0.64. That number comes up yet again. When subtracting that is 0.36. We square that again, it becomes 0.6, and again, multiply by C. So, as you can see, when we have put different observers at different points, they all come up with the same absolute velocity when used with this equation. Okay, so what does that mean? Well, let's look at this number here. We have L of 1, and let's suppose these two numbers are 10 and 11, but just slightly off. So maybe this is a 10.9, and that's, let's say, a 9.9. Now, if we plug that into here, this will make a pretty high number. That's almost the same as 1, or almost the same as L squared. When that gets divided, that becomes a very low number, because, again, this is a 1 subtracting that number. So if this is a really big number, that's almost close to 1, it's a 1 subtracting that number, then this velocity becomes very, very low. On the other hand, if B primed and A primed are so far apart from so different from each other, especially when relative to L, then this number becomes much smaller. And again, it's a 1 subtracting that number, making the velocity much higher. And again, this makes sense. The faster you go, the more length contraction, time dilation you go, and, creating more, a bigger gap in interpretations. The slower you go, on the other hand, the closer everyone's interpretations are. Now, let's take a look at something else. Now, what we do know is that this number here will always be below 1, or between 0 and 1 as a decimal, right? Because L squared will always be longer than the square of these two numbers, because these two numbers are contracted length. So this will be shorter than L, no matter what. So, and there's always a 1 subtracting a number below 1. So this also means several things. One, because this number also cannot be a negative ever. So it'll always be 1 subtracting this. So what does this mean? Well, for one thing, if it's a 1 subtracting a number between 0 and 1, then this number, under the square root, can never go below 0. So again, so this equation will always be definable. Now, if this number could ever get below 0, then obviously you can't do a square root of a negative number. On the other hand, this number also cannot go above 1, because this number here will always be positive. Why is that important? Well, the square root of anything above 1 is higher than 1. That would allow the equation to exceed the speed of light. But notice how no matter what happens, this equation will never exceed the speed of light, because what's under this square root will always be between 0 and 1. And indeed, the speed also cannot be a negative. Okay, so obviously we did some tests with an object that's 10 away. So what if we do something else that's in a completely different distance away? Very simple. Let's suppose there's another point P somewhere in space that's 100 distance away. Now let's calculate. Let's put our numbers in and see if we can get the same velocity back. Okay, so at 100 away, A prime would be 80, because 100, again, assuming there's a 0.6 c motion. For B prime, however, is 80.8, because 100 plus 1, well, we multiply that by 0.8 equals 80.8, and we plug that in. Well, we could do this in our heads. 80.8 subtracted 80 is 0.8. Length is 1. 0.8 squared is 0.64. 1 subtract 0.64, 0.36. That square rooted is 0.6. Again, 0.6e. The same number comes up again. Okay, so I guess one question is that could this be used to calculate the Earth's true velocity through the universe? And even the entire concept of that would be mind-boggling to me. How could that even be doable? But let's just see how we could do that. Okay, the first thing is that we have no way of verifying absolute velocity, right? Because we don't have like a 0 point, we have no omnipotence to figure out what Earth is actually moving, so we can't even verify that. Except there might be a way to do it. And how we do it is simple. If we calculate we use this formula to calculate our absolute velocity, and then we use the same formula to use another point in space to calculate our absolute velocity there, and if the two numbers match, that would mean that this formula is correct. In fact, according to this formula, every single point in space that we can compare ourselves to will always give us the same velocity, regardless of whether that object is moving. So how would this even make sense? So first of all is we would need two observers a distance away from each other, and they would need to have enough distance so we can calculate this gap. Because if they're too close, again, we can't calculate the gap ruler. What do you call this? The gap distance. So now, as I said, we can only use this to calculate the velocity in one orthogonal. The second problem this has is that obviously Earth has a limitation in what we can see. So if we see a star that's 20 light years away, let's say here. Let's say we see a star here. Now, for us to calculate use a second star as a point of reference, that star needs to be on the exact same orthogonal past it, which is naturally not possible. How could we possibly see that? So maybe there's some astronomers can figure out how we could do that. Maybe we can, because here's the thing. If we use another star, then that star will be a different orthogonal to Earth. So the number we come up will be different, right? So it has to be on the exact same orthogonal. Again, I don't know how that's doable. Maybe you could do one star on one side, another star on another side. Now the formula does allow that because this is a square. So even if it's a negative number, that will still become a positive here. So perhaps we can take a look at one direction, and then we take a look at the other direction, the opposite direction. We calculate the absolute velocity from 2 points in space there, and then match those, and then compare those. If those two numbers are exactly the same, or reasonably close, then we can say this formula works. So again, let's see how this would kind of play out. Okay, so again, we would need one orthogonal. Now, one thing is that the Earth itself is moving. So naturally, we cannot, so if we're going this way, taking a look at something over there, imagine this line there. Well, that's not doable because the other person is the opposite side of the Earth. So again, this further complicates things is because Earth is round. So we might need like a ship of some sort or some way of creating a line in which case two observers can look at a third object. So again, you can see here, this is really hard to do because Earth is round. So if let's say this guy here is going to take a look at this object, this star here, this guy will be blocked, right? He's on the other side of that. So again, that'd be much kind of hard to do. So maybe some mathematician can figure out if we can calculate this distance at different times, or through the Earth's sun's rotation, or through the Earth's own rotation. I don't know, maybe there's a way of doing that. Alternatively, it'll be, again, very simple. A long ship, you have one side taking a look from one at a single star, another side taking a look at that star. We get a number, and then we go look at the opposite direction. Now, keep in mind, there needs to be the exact opposite direction because they need to be on the same orthogonal. Because Earth is obviously drifting through space, through something, or to whatever angle. We don't know that. And again, that would only, even if we can match these two numbers, if they're correct, that would only give us the velocity of one orthogonal, right? One dimension, or sorry, one angle. We don't know again, there's a lot more angles to that. So, using something like this, I do think it's almost in the realm of science fiction for now, but in the future, I think we can make some tests to see if we can use this to figure out Earth's absolute velocity. Again, there's probably other challenges to it. The fundamental problem, it has to be a line. But maybe, some super math wizard is going to kind of figure out that we can use whatever fancy calculation to make it we don't need to be in a line. And that would just, further expand on the capabilities of this formula. Okay, so I know that's very complicated and a lot of things to take in, and it kind of disrupts the existing, what we know about relativity. But, do kind of think about it and keep an open mind on this information. Now again, I have some other videos, which is true solution to the twin paradox. This is really the simplest solution to understand. And I have another video about solving the twin ruler paradox. So this is a paradox in which case you have two rulers, or 1 light years in length, and one moves across the other one. And because of that motion, both rulers interpret the other ruler as being shorter. And they supposedly have symmetry, but I kind of solve it and explain why they don't actually have symmetry. This is also a good video, and it's a really good start video to kind of, what it does, it takes snapshots of different t equals different times to let you fully see what exactly is happening. And I really like this video. And I also have another one, which is, this one is about determining which object is moving and which object is stationary. Again. And the other video I have is determining who is in motion with no stationary frame. So in this regard, it's very simple. You are transported to a dimension in which case there's no planets or stars, and there's no way of determining if you're stationary or moving. And then you see another ship moving towards you through this direction, at least through your perspective. How do you determine if you're stationary or the moving one? Or is that even possible? And it is. And that's kind of the prelude to actually getting the full absolute velocity. So again, think of this 3 as sequential. It starts as being figuring out the twin roller paradox, and then we get to determining who is in stationary motion, or who is in motion, who's stationary. And lastly, we get to determining absolute velocity. Again, so if you're kind of getting confused in this video, totally check out the other videos and see if you can get them, if you can grasp them, or you disagree, and that's fine too. I'm totally open to debate on how these things work and how these numbers add up. Okay, so thanks for watching. Please share.